Picture, for a moment, the quiet arithmetic happening under the sole of a boot. A body's weight, all of it, channeled downward through two narrow points of contact, meeting a surface that looks, from above, perfectly solid. And yet, something in that meeting point is not quite what it seems. Somewhere in that thin zone between rubber and crystal, a transformation is taking place that most people never think to ask about. A transformation so fast and so small that it hides in plain sight every winter, on every pond, on every sidewalk left unsalted after a cold night. You do not have to be standing on it right now for this to matter. Even hearing about it, even picturing it, is enough to start loosening something in the mind, the kind of loosening that makes sleep feel a little closer. This is a story about ice, but it is also a story about a question that turns out to be much stranger than it first appears, a question that scientists have been quietly circling for more than 150 years without fully agreeing on the answer. Why is ice slippery? It sounds like the kind of thing a child would ask and an adult would answer in one sentence. Something about pressure, maybe, or something about cold. But the closer you look, the more the simple answers start to slide away from you, the way your foot might on a frozen driveway, and what is left is a genuinely open scientific puzzle, one that touches on crystal structure, on the strange behavior of water molecules, on friction, on heat, and on a layer of matter so thin that for most of history no one even suspected it was there. Let's start with the feeling itself, because the feeling is where all good questions about the world begin. Think of the last time you stepped onto ice, maybe a frozen puddle on a morning walk, maybe a skating rink, maybe just a patch of black ice you didn't see until your foot was already sliding. There is a particular quality to that slipperiness that is different from other kinds of slipperiness. Wet soap is slippery, but you know why. There is a film of soap and water between your skin and the tub. A polished wood floor in socks is slippery, but you understand that too. Low friction between two smooth, dry materials rubbing against each other. Ice feels different. It feels slippery, even when it looks bone dry. It feels slippery, even in weather so cold that any liquid water on the surface should have frozen solid the instant it touched the air. And that contradiction, dry to the eye but wet to the foot, is the seed from which more than a century of scientific argument has grown. The first person to take this seriously in a formal, scientific way was a man named Michael Faraday, working in London in the middle of the 19th century. A scientist better remembered today for his work on electricity and magnetism than for his curiosity about frozen water. But Faraday noticed something small and strange. He noticed that when two blocks of ice were pressed together, even at temperatures well below freezing, they would fuse into a single piece. Not melt in any obvious sense, not turn to liquid and refreeze, but simply merge, as though there were some thin film of something between them that allowed the two solid surfaces to bond. Faraday called this quality regelation, from Latin roots meaning to refreeze, and he suspected, correctly as it turned out, that there was more going on at the surface of ice than the eye could see. He did not have the tools to explain it fully. Nobody in his era did, but he had noticed the doorway, even if he could not yet walk through it. For a long time after Faraday, the explanation that most people settled on had to do with pressure. The idea went something like this. When you stand on ice, your body weight is concentrated onto a very small area, especially if you are wearing something like a skate blade, which touches the ice along a line only a few millimeters wide. All that weight pressing down into such a tiny area creates enormous pressure at the point of contact, and according to a well-known property of water, increased pressure can lower the melting point of ice. Push hard enough, the reasoning went,
and you push the melting point below the actual temperature of the ice, so a thin film of liquid water forms right beneath the blade. You glide across that film, and the moment the pressure is released, the water refreezes behind you. It is an elegant story. It has been taught in classrooms for generations. It shows up in encyclopedias, in ice skating instructional pamphlets, in the kind of casual explanation a parent might give a child on a car ride home from the rink. There is only one real problem with this story, and it is the kind of problem that tends to unravel a beautiful idea the moment someone bothers to do the arithmetic. The amount that pressure can lower the melting point of ice is actually quite small. To melt ice by pressure alone, you would need to apply an extraordinary amount of force over an extraordinarily small area, more than what an average skater's body weight, even concentrated onto a thin blade, can actually generate. Researchers who worked through the numbers carefully, decades after that pressure story first took hold, found that the pressure explanation predicted only the faintest melting, nowhere near enough to explain how effortlessly a skater glides, and nowhere near enough to explain why ice feels slippery, even to someone simply standing still on it in flat shoes, where the pressure per square inch is nothing like a skate blade's edge. And here is the detail that quietly finishes off the pressure explanation altogether. Ice is slippery, even when you are not applying much pressure to it at all. A dropped coin will slide across a tilted patch of ice. A curling stone, spread across a wide flat surface, with very little weight per square inch, glides remarkably far with a gentle push. If pressure alone were responsible, these low-pressure situations should barely be slippery at all, and yet they are. So if it is not simply pressure squeezing out a film of meltwater, something else has to be happening. And this is where the story gets genuinely interesting, because it turns out the answer may not be a single, tidy mechanism at all, but several different effects layered on top of each other, each contributing something, none of them the whole picture by itself. One of those effects has to do with something scientists now call a quasi-liquid layer, an almost impossibly thin skin of disordered, loosely arranged water molecules that seems to exist on the surface of ice even when the ice itself, just a few molecules deeper, is locked into a rigid, orderly crystal structure.
This layer is not liquid in the way water in a glass is liquid. It is something stranger, something in between. Molecules that are neither fully bound into the crystal lattice, nor fully free to move as a liquid would. And this layer appears to exist not because of the pressure of a passing skate or a passing foot, but simply because ice, sitting quietly in the cold, behaves that way on its own, all the time, everywhere its surface meets open air. Another piece of the puzzle involves simple friction, the ordinary kind, the rubbing of one surface against another, generating heat the way rubbing your hands together on a cold day generates warmth. As a blade, or a shoe, or a sliding object moves across ice, the friction of that motion itself creates a small amount of heat right at the point of contact, and that heat can be enough to melt a very thin film of the ice directly beneath it, quite apart from any pressure effect. This means the very act of moving across ice can be part of what makes it slippery to move across, a kind of feedback loop where motion begets a little melting, and that melting in turn makes the motion smoother. What is remarkable, lying here thinking about it, is how ordinary and how strange this all is at once. Ice is one of the most familiar substances in daily life, something children learn to recognize before they can talk, something that forms in every freezer, on every winter morning, on the surface of nearly every body of still water in a cold climate. And yet, beneath that familiarity is a surface so subtle, so quietly active, that it took physicists more than a century,
Working with instruments Faraday could never have imagined to even begin describing it properly. There is something soothing in that thought, the idea that the world still holds small, patient mysteries in the most everyday of places, mysteries that do not need to be solved tonight or ever, in order for you to rest easy, knowing they are there. Before we go further into what that thin layer on the surface of ice is actually made of, and why it seems to exist even in weather cold enough to freeze almost anything else in sight, it is worth pausing to imagine, one more time, that quiet moment of contact between something solid beneath you and something almost imperceptibly softer, resting just above it, waiting there in the cold, unnoticed by nearly everyone who has ever walked across it.
Let's start, then, by setting ordinary friction aside for a moment and asking a more basic question, one so basic it almost feels foolish to ask out loud. Why does anything resist sliding at all? Why can you not simply glide your palm across a wooden tabletop the way a puck glides across ice? The answer, when you look closely enough, is that no surface is ever truly smooth. Not the tabletop, not your palm, not the sole of a shoe, not even a pane of glass that looks perfectly flat under ordinary light. If you could shrink yourself down to the size of a dust mote and walk across what appears to be a polished countertop, you would find yourself climbing over hills and dropping into valleys, an entire landscape of jagged peaks, too small for any human eye to register. Engineers who study this kind of thing call it surface roughness, and it exists on almost everything, a permanent, invisible topography etched into the material by the way it was formed, cut, poured, or cooled. When two such surfaces meet, they do not actually touch everywhere they appear to touch. They touch only at the tips of their tiny peaks, and only some of those peaks, at that. The rest of what looks like solid contact is really open space, gaps and air pockets, far too small to notice, but very real all the same. It is a little like turning two upside-down egg cartons toward each other and pressing them together. The bumps catch the bumps, and the whole arrangement locks together in a rough, uneven way, resisting any attempt to slide one carton across the other. That interlocking, multiplied across billions of microscopic points of contact, is a large part of what we experience as ordinary friction, the drag that makes a wooden crate scrape and catch as you push it across a floor, the resistance that lets your shoes grip a dry sidewalk. There is a second ingredient, too, one that is a little less intuitive, and it has to do with adhesion, a kind of gentle, momentary clinginess between materials. At the scale of atoms and molecules, surfaces that touch do not merely bump against each other, they also attract each other, however faintly. This is the same family of forces, generally speaking, that lets a gecko cling upside down to a ceiling, or that makes two pieces of very clean, very flat glass seem to stick together if you press them just right. Under ordinary conditions, this adhesive pull between everyday objects is usually so slight that we never notice it at all. It is overwhelmed by the much larger effect of that interlocking roughness. But scientists studying friction in careful detail, going back to work done in the 18th century by a French physicist named Charles-Augustin de Coulomb, and refined many times since, have found that adhesion is always there in the background, adding just a little more resistance to sliding than roughness alone would explain. Coulomb, incidentally, is a name many people associate with electricity, since a unit of electric charge bears his name, but long before that, he spent years rolling blocks of wood and metal across each other,
trying to work out the basic laws that govern how one surface slides, or fails to slide, over another. So picture, for a moment, an ordinary block of wood resting on an ordinary wooden floor. To push it sideways, you have to do two kinds of work at once, without ever really separating them in your mind. You have to force those microscopic peaks to climb up and over one another, breaking the countless tiny interlocks, holding the surfaces together, and you have to overcome the faint mutual pull of the atoms themselves, however small that pull may be. Both of these things take energy, and both of them show up to your muscles as resistance, as drag, as the ordinary effort of getting something to move. Now here is where ice begins to seem peculiar. If you performed the very same test with a block of ice resting on a smooth, cold surface, you would still find some resistance at very cold temperatures, but under many everyday conditions, especially anywhere close to the melting point, that resistance turns out to be far smaller than you would predict just by measuring how rough the ice looks, or how sticky its molecules ought to be. Something is quietly canceling out part of the drag that ordinary physical intuition says should be there. It is as though ice is somehow cheating the rules that every other solid seems to follow so faithfully. And what makes this even more puzzling, rather than less, is that ice does not behave this way consistently. Slide across ice at one temperature, and it feels wonderfully slick, almost frictionless, the way a rink feels to a skater gliding at speed on a cold winter evening. Slide across ice at a much colder temperature, on a still, dry, deeply frozen lake far from any city, and it can feel almost like sliding across fine sandpaper, gritty, reluctant, dragging at your boots, with something close to ordinary friction.
Change the pressure, pressing down on the ice. Change the speed at which something moves across it. Change whether the ice is touching rubber, or steel, or another sheet of ice, or bare skin, and the slipperiness seems to shift again, sometimes by a little, sometimes quite dramatically. It is not one fixed property of the material, the way the color of a rock is a fixed property, or the way the hardness of a diamond stays the same no matter who is scratching it. Slipperiness, in the case of ice, behaves more like a mood, changeable, responsive, sensitive to circumstances in a way that most solids simply are not. This is, in its own quiet way, one of the more delightful oddities hiding inside something so plain and so common. We tend to sort the physical world into tidy categories without thinking twice about it. Solids are solids, we assume, fixed and dependable, obeying one consistent set of rules from one encounter to the next. Liquids are liquids, flowing and shapeless, offering almost no resistance to objects moving through them. Ice, stubbornly, does not sit neatly inside either category. It holds its shape like any proper solid, keeps its crystalline structure, shatters if you strike it hard enough with a hammer, and yet, at its very surface, in that impossibly thin zone where the solid ends and the surrounding air begins, it seems to borrow a little something from the liquid world, a faint slipperiness that comes and goes depending on conditions, refusing to commit fully to either state. It helps, perhaps, to think of this the way you might think of a person who is mostly quiet and reserved, except in one narrow set of circumstances, where they suddenly become unexpectedly playful. The bulk of who they are, most of the time, in most situations, stays steady and predictable. But there is this one particular context, this one particular trigger, where something else entirely comes forward,
something that does not seem to match the rest of their character at all, and yet is unmistakably part of them too. Ice, in its depths, is entirely dependable, a rigid lattice of water molecules locked into place, cold and solid and unyielding. But right at its outer skin, under the right conditions, it becomes something else, something that behaves almost like a very thin film of liquid, and it is that outer skin, that razor-thin boundary, which turns out to matter enormously for anything sliding across it.
So we are left, for now, holding several separate threads at once, each one true, each one only part of the answer. There is the ordinary roughness and adhesion that governs sliding for almost every material on Earth. There is the strange way ice sometimes seems to slip past those rules rather than obey them. There is the fact that this slipperiness changes with temperature, with pressure, with speed, with whatever happens to be touching the ice at that particular moment. And underneath all of it lies that thin, quiet layer at the surface, waiting to be examined more closely, waiting to explain, piece by piece, why something so cold can feel, under just the right conditions, almost impossibly smooth. To understand that thin, quiet layer at all, we have to go smaller than ice, smaller than water itself, down to the shape of a single molecule, because everything that happens later, all the slipperiness and all the strangeness, starts here, in a shape so small you could fit billions of them into the period at the end of a sentence. A water molecule is built from one oxygen atom and two hydrogen atoms, and if you have ever seen it drawn on a chalkboard or a page, you probably remember it as a kind of loose V, oxygen at the vertex, hydrogen splayed out to either side. That picture is not just a simplification for students. It is genuinely the shape, more or less, that the molecule takes, and the reason for that shape has to do with the way oxygen holds onto its electrons. Oxygen is a somewhat greedy atom, in the specific sense that chemists mean when they talk about electronegativity. It pulls the shared electrons in each bond a little closer to itself, away from the hydrogens, and it also carries two pairs of electrons of its own that are not involved in bonding at all, just sitting there, repelling everything nearby the way any negatively charged region would. Those unshared pairs push the two hydrogen atoms away from each other and away from a straight line until they settle into an angle of about 104.5 degrees. Not quite the right angle of a square corner, not the wide, flat angle you would get if the molecule were a straight line. Something in between, something bent, something a little lopsided. That bend turns out to matter more than almost anything else in this whole story, because it means the molecule ends up with two slightly different faces. Down near the hydrogens, the molecule carries a faint positive charge because those electrons have been tugged away toward the oxygen. Up near the oxygen, especially near those two lone pairs, the molecule carries a faint negative charge. The whole thing is still electrically neutral if you added up every charge inside it, but the charge is not spread out evenly. It is lopsided, the way a bar magnet is lopsided, with a north end and a south end, except here, the two ends are electrical rather than magnetic. This lopsidedness has a name. Chemists call it polarity, and a molecule shaped this way is called a polar molecule. It is worth sitting with that word for a moment, polar, because it will keep resurfacing, quietly, underneath everything else we talk about tonight. Now, a single polar molecule, floating alone, in some imaginary empty space, would not be especially interesting. The interesting part begins when you put many of them together, because the positive end of one molecule, that faintly charged region near its hydrogens, finds itself attracted to the negative end of a neighboring molecule,
that faintly charged region near its oxygen. This attraction is not a full chemical bond in the way that holds the hydrogen and oxygen together within a single molecule. It is gentler than that, a kind of electrical handshake rather than a permanent grip, and scientists call it a hydrogen bond. The name is a little misleading because it can make you think of it as being just as strong as an ordinary bond, and it is not. It is weaker, more temporary, more like a friendship that forms and dissolves and reforms than like a marriage. But it is also far from nothing, and in water, these hydrogen bonds are constantly forming, breaking, and reforming again, molecule to molecule, in a restless, flickering network. Here is a way to picture it that might help settle the image in your mind before sleep starts to take over the shape of your thoughts. Imagine a very large ballroom, dim and quiet, filled with dancers, and each dancer has two hands reaching outward, and at the same time, two shoulders that other dancers can reach for. In liquid water, the dancers keep changing partners, reaching, connecting, letting go, reaching again, and the whole floor is in gentle, constant motion, no pattern holding steady for more than a fraction of a second. That restlessness, that endless changing of partners, is part of why liquid water flows the way it does, why it takes the shape of whatever container holds it, why you can move your hand through it without resistance. But cool that ballroom down, take away enough of the energy that keeps the dancers moving so freely, and something changes. The dancers slow down enough that they can finally hold on to their partners instead of constantly losing their grip. And because each water molecule has exactly two hydrogens to offer, and two lone pairs to receive, each molecule can, in principle, hold hands with four neighbors at once, two through its hydrogens, two through its oxygen. When the temperature drops low enough, down to that specific threshold we call the freezing point, the molecules stop rearranging fast enough to remain a liquid, and they lock into a repeating pattern built around this four-way handshake, each molecule bonded to four others, over and over, throughout the whole sample. That locked repeating pattern is what we call ice, or more precisely, it is what we call one particular kind of ice, the ordinary kind that forms around us at everyday pressures, which crystallographers refer to as hexagonal ice. Because if you could shrink yourself down and look at the arrangement from just the right angle, you would see six-sided rings of molecules repeating outward in every direction, the same six-sided symmetry that, much later, shows up in the shape of snowflakes, magnified 1 billion times over into something visible to the eye.
Here is the detail that tends to surprise people, even people who have lived their whole lives around ice, without ever asking why it behaves the way it does. That four-way handshake, that tidy arrangement where each molecule reaches for exactly four neighbors, is not a compact arrangement. It is, in fact, remarkably open, full of small gaps and hollow spaces, because a bent molecule reaching out in four directions at fairly wide angles cannot pack together as tightly as, say, marbles poured into a jar. In most substances, when a liquid cools and solidifies, the molecules settle closer together, because solids are generally the more tightly packed state, the more efficiently arranged state, and that tighter packing is exactly why most solids sink in their own liquid. But water is unusual, because the specific geometry demanded by its hydrogen bonds forces the molecules into a lattice that is actually less crowded than the liquid it froze from. In liquid water, molecules are jostling and slipping past one another, and even though they are connected by hydrogen bonds much of the time, those bonds are short-lived enough, and the molecules disorganized enough, that they can still crowd in fairly close together, filling space with reasonable efficiency. Freeze that same water, and force every molecule into the rigid, four-armed handshake of the crystal, and suddenly the whole structure has to expand outward to make room for that lattice, opening up all those small hexagonal gaps. The result, measured simply and directly,
is that a given mass of ice takes up more space than the same mass of liquid water. Ice is, in that specific sense, roomier than water. That is why ice floats. That is why a bottle of water left too long in a freezer will crack its own container, the expanding lattice pushing outward with a quiet, patient force, strong enough to split glass or plastic. That is why lake ice forms a floating cap over liquid water beneath it in winter, insulating the water below, allowing fish and other creatures to survive a season that would otherwise freeze them solid from the bottom up. So the interior of ice, the deep, ordinary bulk of it, is this open, airy, four-connected lattice, every molecule reaching for its four partners, locked into a pattern that repeats with the patience of wallpaper, unrolling the same motif endlessly in 3 dimensions. It is a structure built entirely on the logic of completion, every hydrogen finding an oxygen to reach toward, every lone pair finding a hydrogen to receive. But now think about what happens at the very edge of that lattice, at the outermost layer of molecules, the ones facing not another neighbor but simply open air.
A molecule in the depths of the ice has 4 partners waiting on every side, above, below, and around, the pattern continuing symmetrically in all directions. A molecule sitting right at the surface does not have that luxury. On one side, it still has neighbors reaching back into the crystal. On the other side, there is nothing, just empty space, or air, or whatever happens to be resting against the ice. It cannot complete its full set of 4 hydrogen bonds, because there is simply nothing there to bond with on that outward-facing side, and a molecule left with an incomplete handshake behaves differently than one whose hands are all full, which is exactly the small, quiet imbalance we will need to follow more closely next. Picture standing at the edge of a very large, very orderly garden party. Everyone around you is holding hands with 4 other people, a neat closed ring of arms, and you can feel the whole crowd swaying together in that locked, patient way that groups do when everyone is anchored. Now imagine you happen to be standing at the very last row right against the fence. You still have 2 or 3 hands to hold on your inward side, but the hand you would normally extend outward has nothing to grasp. There is only open air past the fence. What do you do with that free hand? You cannot simply let it hang perfectly still, because nothing is holding it in place from that side. It drifts a little. It taps against your leg. It moves in small, restless ways that the hands deeper in the crowd, fully occupied on every side, never have the freedom to move. This is roughly the situation for a water molecule sitting at the very surface of a piece of ice. Deep in the bulk of the crystal, as we've been picturing, every molecule has completed its full set of 4 hydrogen bonds, reaching out symmetrically in every direction, held in place by partners above and below and around. But a molecule at the outermost surface is missing some of those partners simply because there is nothing there to bond with. Past that molecule is air, or maybe a thin film of water, or the surface of someone's tongue, or the sole of a boot. There is no crystal on that side to reach into. And so, just like that free hand at the edge of the garden party, the surface molecules of ice are left a little unanchored. They still have some bonds pulling them into the lattice below, but on the open side, they have nothing to hold them rigidly in place, and so they wobble, they vibrate, with a bit more freedom than their fully bonded neighbors deeper inside. They can shift position slightly, rotate a little, exchange places with the molecule next to them in ways that a molecule locked into all 4 bonds simply cannot. This gives rise to something that researchers, going back more than a century and a half, have called by many different names. Michael Faraday, the same scientist we mentioned earlier pressing two blocks of ice together and watching them fuse, was among the first to notice something odd about the surface of ice specifically, something that seemed to behave less like a rigid solid and more like it was coated in the faintest film of liquid, even when the temperature was safely below freezing. He didn't have the tools to explain exactly what he was seeing, not in the molecular detail we now have access to, but he described the phenomenon carefully, and it stuck with people, this puzzling observation that ice seemed to have a kind of skin that behaved differently than the ice underneath it. Today, this is often called the quasi-liquid layer, sometimes the pre-melt layer, sometimes just the disordered surface region, depending on which scientist you ask and which decade of research they're drawing from. The names vary a little, and so does the exact way people describe its thickness and behavior, because this is one of those areas of ice science that continues to be actively studied and occasionally debated, not something settled once and filed away. But the basic idea, stripped down to its simplest form, is something like this. Even when the bulk of a piece of ice is safely locked into its ordered, four-connected lattice, the outermost few layers of molecules, right at the boundary between ice and whatever touches it, are more mobile, more disordered, more liquid-like in their behavior than the solid interior beneath them, not fully liquid, not sloshing and flowing the way water in a glass would, but not perfectly rigid either. Something in between, something that has enough looseness to let molecules slide past each other a little, to rearrange, to behave with more freedom than the strict geometric prison of the full lattice would normally allow. It helps to think of it almost like the surface of a mostly frozen pond that hasn't been touched by anyone yet. If you look at it from a distance, it looks solid, uniform, a single continuous sheet. But if you were small enough to stand right at the very top layer of that ice, you might notice it isn't quite as still as the ice a few inches down. There's a faint give to it, a softness that has nothing to do with actual melting in the ordinary sense, and everything to do with those missing outward bonds we were just picturing, all up and down the surface, molecule after molecule, each one a little untethered on its open side. This quasi-liquid layer isn't a fixed, unchanging thing either. It responds to temperature in a way that makes intuitive sense once you sit with it for a moment. As ice warms, getting closer and closer to its melting point without actually crossing that threshold, this mobile surface layer tends to thicken. More molecules near the surface pick up that same restless, half-bonded quality, and the layer of disordered, liquid-like behavior extends a little deeper into what would otherwise be solid crystal. Cool the ice back down, push the temperature further from the melting point, and the layer tends to thin back out, the molecules settling back closer to that fully ordered, fully bonded state, more of them regaining their full four-way handshake as the thermal jostling that was loosening them starts to calm. And it isn't only temperature that shapes this layer. What actually touches the ice matters too. A perfectly clean surface of ice, resting against nothing but still air, behaves one way, but ice rarely exists in that kind of pristine isolation, does it? Ice on a sidewalk has dust settled into it, tiny particles of salt or grit or pollen. Ice in a glacier has trapped air bubbles and mineral dust carried by wind from thousands of miles away, sometimes from deserts on the other side of the planet, sealed in over centuries. Ice on a window has the faint residue
of whatever was in the air of the room, condensed and frozen in place. Even something as simple as ordinary table salt, scattered across an icy path in winter, changes the behavior of that surface layer dramatically, drawing more of the ice into that mobile, disordered state at temperatures where it would otherwise have stayed more firmly locked, which is precisely why people scatter salt on icy steps in the first place, a practice that stretches back long before anyone understood the molecular reason it worked.
So this thin, mobile skin at the boundary of ice is not one fixed thing with one fixed thickness, but something that shifts and responds, thickening and thinning with warmth and cold, changing character depending on whether the ice is touching clean air, or dusty air, or salt, or the warm skin of a hand. It's shaped by its surroundings the way the surface of a pond ripples differently depending on the wind that day, never quite the same twice, always responding to something just outside itself. Why does any of this matter for the question of slipperiness? It matters because for a very long time, this quasi-liquid layer was treated by many scientists as the leading explanation, the answer that seemed to tie everything together so neatly that people stopped looking much further. If the very surface of ice is always coated in this loose, mobile, liquid-like film, even when nothing is pressing down on it, even when no skate blade or boot sole has come anywhere near it, then perhaps that thin film alone is enough to explain why ice feels slippery to the touch. No pressure melting required, no friction heating required, just the ice itself, quietly maintaining its own faint, restless skin at every boundary, all the time, regardless of what comes along to slide across it. It's a tempting idea, and a partially true one, but as with the pressure explanation before it, and the friction explanation before that, it turns out this quasi-liquid layer is not quite the whole story either, and understanding exactly how thick that layer really is, and exactly how slippery a few molecular layers of restless water can actually make something feel, turns out to be a more delicate question than it first appears. Let's go back, for a while, to an idea that came earlier than the quasi-liquid layer, an idea that most people still carry around without ever having examined it closely, because it was taught so early and so confidently that it settled into the mind like a fact rather than a hypothesis. This is the idea that skating works because the blade presses down on the ice, and that pressure alone squeezes the ice into melting beneath it, producing a thin film of liquid water exactly where the blade needs it, and vanishing again the instant the blade has passed. It's a beautiful, tidy picture. A person's weight becomes a kind of key that unlocks water from solid ice, just for a moment, just in the right place, and then the door closes again behind them. For over a century, this was the explanation offered in classrooms, in encyclopedias, in the quiet confidence of textbooks that didn't feel the need to show their work. The idea has real physics behind it, and it isn't nonsense, so it deserves to be walked through slowly and fairly before its limits are gently exposed. Ice is one of those unusual substances, water being unusual in many ways, where the solid form is less dense than the liquid form. Ordinary things get denser when they freeze. Wax, iron, most rocks, most metals, they all contract and pack tighter as they cool into a solid. Water does something backward. When it freezes, its molecules arrange themselves into a hexagonal lattice, each molecule holding hands with its neighbors at wide, open angles, and this open lattice actually takes up more room than the liquid does. That's why ice floats, and it's also why an ice cube left too long in a full glass will nudge water over the rim, and why a bottle of soda, forgotten in a freezer, can split itself open with a sound like a small firecracker, because the water inside wanted to expand into a spacious crystal, and there was nowhere for that new bulk to go. Now think about what happens if you squeeze that lattice. If ice takes up more room than an equal mass of water, and you push hard on the ice from outside, you are, in a sense, arguing with its shape. You are telling it there isn't as much room as it wants. And under the right conditions, ice will respond to that argument by giving up its spacious lattice and collapsing back into the denser, more compact liquid form, because the liquid form fits more easily into a smaller space. This is the essence of pressure melting. Squeeze ice hard enough, and you can nudge its melting point downward, coaxing it to melt at a temperature where, left alone, it would have stayed perfectly solid. This is closely related to something called regulation, a word that sounds almost invented for a lullaby, all soft consonants and looping syllables. Regulation is the phenomenon where ice melts under pressure, and then, once that pressure moves on or is removed, it refreezes again almost immediately, the water returning to solid form as though it had never left. There's a classic old demonstration, one that traveled through physics lecture halls for generations, where a fine wire, weighted down at both ends, is draped over a block of ice. Slowly, over the course of an hour or more, the wire sinks down through the block, cutting a thin channel as it goes, because the pressure of the wire melts the ice directly beneath it. But here is the quietly strange part. The wire doesn't leave a trench behind it. As it passes through, the water above the wire, no longer under that concentrated pressure, refreezes, closing the gap again. By the time the wire has worked its way all the way through and dropped out the bottom, the ice block looks whole again, uncut, as if nothing had ever passed through its middle at all. It's the kind of thing that feels almost like a magic trick performed by physics itself, a solid healing itself in slow motion. So the pressure story is not imaginary, it's demonstrable, and it was demonstrated, carefully, by serious scientists, some of them working in the 19th century when the tools for measuring such delicate effects were nowhere near as refined as they are now. And it made intuitive sense to extend that story to skating. A skater stands on a blade, and a blade is narrow, so all of that person's weight is concentrated onto a very small area of ice, a strip perhaps only a millimeter or two wide. A concentrating weight onto a small area increases pressure, in the same way that a person in stiletto heels can dent a wooden floor that would never be dented by the same person's weight spread across the flat sole of a sneaker. It isn't the total weight that matters so much as how small an area that weight gets divided into. So it seemed only reasonable that a skater's blade, pressing down hard onto a thin edge of ice, might be melting a thin film beneath itself just enough to glide, and that this film would refreeze as quiet regulation the instant the blade moved on, the same way the wire's channel closed up behind it. But here is where the arithmetic quietly refuses to cooperate, and it's worth sitting with the numbers for a moment, not to memorize them, but just to feel their shape, because there's something satisfying about watching a tidy explanation meet a stubborn fact. To lower the melting point of ice by pressure alone takes a surprising amount of force. Roughly speaking,
And different sources give slightly different figures depending on conditions. You need something on the order of 100 to 130 atmospheres of pressure just to lower the melting point of ice by a single degree Celsius. An atmosphere, for reference, is roughly the pressure the air around you is already exerting on your skin at sea level, all the time, pressing in from every direction, so ordinary and constant that a person never feels it as pressure at all, only as the simple fact of being alive under a sky. To need over 100 atmospheres just to shift the melting point by 1 degree is to need an enormous amount of squeezing for a very small reward. Now picture an average adult skater, a reasonably light person, distributing their weight across the narrow strip of a skate blade. Even accounting for how thin that blade edge is, even granting the concentrated pressure that comes from a small contact area, careful calculations, the kind done by physicists sitting with pencils in patience rather than skating themselves, show that a typical skater generates something in the neighborhood of only a few dozen atmospheres of pressure beneath the blade, not the many hundreds that would be needed to meaningfully melt ice on a cold day. If the air temperature is only a couple of degrees below freezing, pressure melting alone might, just barely, explain a very thin film. But skating happens, and happens easily, at temperatures far colder than that. People skate comfortably on ponds and rinks when the air is 10 degrees below freezing, 20 degrees below freezing. Temperatures at which the pressure a skater's weight can generate falls hopelessly short of what the arithmetic demands. The numbers simply don't stretch that far. It's a little like discovering that a key you were sure unlocked the door turns out to be the wrong size for the lock. Close enough to seem promising, but not close enough to actually work. And this gap becomes even more obvious once you think beyond skating, to the more ordinary, more universal experience of simply walking across an icy patch and feeling your feet slide out from under you, or setting a hand down on a frosted railing and feeling how little grip it offers. A boot sole is nothing like a skate blade. It's broad, it's flat, it spreads a person's weight across a wide area rather than concentrating it into a thin edge, which means the pressure generated underfoot in ordinary walking is smaller still than what a skater achieves, sometimes by a very wide margin. By the arithmetic of pressure melting, an ordinary boot pressing down on ice should barely disturb it at all, and yet ice under a boot still feels unmistakably slippery, still sends people's feet skating out sideways in exactly the way that has nothing to do with narrow blades or concentrated edges. If pressure melting were the whole explanation, walking on ice in flat shoes ought to feel far more secure than it does, and it simply doesn't. So the pressure story, elegant as it is, turns out to explain only a small and special corner of the larger puzzle, and even there its numbers strain and stretch further than they can comfortably reach.
Something else has to be doing most of the quiet, invisible work. Something that doesn't depend on how narrow a blade is or how much a person weighs. Something present even for a bare, wide, ordinary human hand resting flat against ice on a cold and windless afternoon. So let's set pressure aside for a while, the way you might set aside a tool that turned out to be the wrong shape for the job, not thrown away, just placed back in the drawer, because it will matter again later in ways we haven't gotten to yet. For now, let's turn toward a much simpler and much more universal idea, one that doesn't care whether you're wearing a skate blade or a flat boot sole or nothing at all, one that shows up the moment two surfaces move against each other, no matter how wide or narrow the contact happens to be. That idea is friction itself, not friction as an obstacle, but friction as a kind of engine, a small and humble converter that takes the effort of motion and turns a portion of it into heat. Think for a moment about rubbing your hands together on a cold morning. You do this instinctively, without needing to have studied any physics at all, because somewhere in the accumulated experience of being a warm-blooded creature, you already know that pressing your palms together and sliding them back and forth will make them warmer. Nothing is burning. There's no flame, no external source of heat being added from outside, and yet warmth appears, seemingly from nowhere, generated entirely by the motion itself. If you rub slowly, the warming is faint, almost too subtle to notice. If you rub quickly, briskly, with real insistence, the warmth builds fast enough that you can feel it climbing within seconds. The faster the motion, the more heat appears. This is not a coincidence, and it's not a separate phenomenon from what happens on ice. It's the same underlying idea, just easier to feel directly because your palms are so sensitive to temperature and your own effort is so easy to notice. What's actually happening, at a level too small to see, is that the microscopic bumps and ridges on your skin are catching against the microscopic bumps and ridges on the opposite palm, and every tiny catch and release, every tiny snag, as one rough patch drags across another rough patch, requires a bit of mechanical work. That work doesn't vanish. Energy doesn't simply disappear when a snag lets go. It has to go somewhere, and where it goes, again and again, in countless tiny events happening all across the contact area at once, is into the random jostling motion of the atoms right at the surface. That jostling, that agitation, is what temperature actually is at the smallest scale. So heat isn't some separate substance being injected from outside. Heat is simply what mechanical motion turns into once it's forced through the resistance of two surfaces sliding against each other. Now carry that same idea over to a skate blade crossing a sheet of ice, or a boot sole scuffing forward across a frozen puddle, or even just a bare hand being dragged flat across a frosted railing. The physics doesn't change just because the surface is ice instead of skin. Ice, at the microscopic scale, isn't actually smooth in the way it looks from a few feet away. Under enough magnification, even ice that appears mirror flat to the eye reveals itself to be a landscape of tiny irregularities, small crystalline ridges and imperfections left over from however the ice happened to freeze. When something slides across that landscape, whether it's a blade or a sole or the pad of a finger, those irregularities catch and drag and release in exactly the same way your palms do, generating friction, and that friction generates heat, right at the surface, right at the thin sliver of contact where motion is actually happening. And this is the piece that starts to feel almost paradoxical if you don't slow down and think it through carefully, because the surrounding air might be bitterly cold, 10 degrees below freezing, 20 degrees below freezing, cold enough to make your breath fog and your fingers ache within moments of stepping outside without gloves. And yet none of that ambient cold has any say over what happens in that impossibly thin layer where a moving object is actually touching the ice. That contact layer is its own small, isolated world, generating its own heat locally, independent of what the thermometer nailed to the porch happens to read. The air can be ferociously cold, and the bulk of the ice can be ferociously cold, and still, right where the sliding is actually occurring, in a region so thin it would be almost impossible to measure directly, the temperature can be pushed upward, sometimes just enough, sometimes exactly enough, to nudge that razor-thin layer of ice past its melting point and into liquid water,
if only for the briefest of instants. It helps to think about how narrow and specific that heated region really is. When you rub your hands together, the warmth you feel doesn't spread evenly through your whole body, doesn't raise the temperature of your elbows or your shoulders. It stays concentrated almost entirely in the skin that's actually doing the rubbing, dissipating outward from there, fading as it moves away from the source. The same concentration happens at the interface between a moving object and ice. The heat isn't generated everywhere in the ice at once. It's generated only along the seam of contact, only in that vanishingly thin skin where motion is actively occurring, which means it can be intense enough, right there, to matter, even while the ice just a fraction of a millimeter below remains every bit as hard and cold and solid as it was before anyone touched it. Speed turns out to matter enormously here, in a way that lines up neatly with the hand-rubbing example, and this is worth sitting with for a moment, because it explains something that might otherwise seem strange. A person standing still on ice, simply resting their weight without moving at all, generates essentially no frictional heat, because there's no sliding happening, no motion converting into warmth.
It's only once something begins to move, once a blade begins to glide, or a boot begins to scuff, or a hand begins to slide along a railing, that the friction engine switches on and starts producing heat as a byproduct of that motion. And the faster the motion, generally speaking, the more heat gets produced per moment, which is part of why a skater, gliding briskly across a rink, can maintain a slick, cooperative surface beneath their blades in a way that someone shuffling along at a crawl might not manage nearly as well. Motion is the ignition switch, and the vigor of that motion helps determine how strong the resulting flame, so to speak, actually burns, even though nothing is burning at all in the literal sense. Contact area plays its own quiet role alongside speed, and it's worth noticing that it pulls the story in the opposite direction pressure did. Where pressure melting favored a narrow, concentrated contact, like a thin skate blade, frictional heating doesn't need narrowness in the same specific way. It needs enough contact for meaningful rubbing to occur, and it benefits from surfaces that actually catch against each other rather than gliding past with almost no interaction at all. A hand dragged flat across a frosted railing has a much broader contact area than a skate blade does, and yet it can still generate a faint, perceptible warming, can still coax the thinnest whisper of moisture out of the frost beneath it, because the friction engine doesn't require a blade's narrowness to function. It only requires motion, resistance, and enough contact for that resistance to do its quiet work. This is one of the reasons frictional heating manages to reach so much further than pressure melting ever could, covering boots and gloves and bare skin and sled runners alike, rather than being confined to the special case of a narrow blade under a skater's full weight. There's something almost comforting in realizing that the warmth generated this way is entirely self-produced, summoned into being by the object itself rather than borrowed from anywhere else. Nothing about the surrounding winter air changes. Nothing about the deep, structural coldness of the ice changes either, not down at any depth beyond that thin working layer where the sliding is actually happening. The cold stays exactly as cold as it was a moment before, everywhere, except in that fleeting, self-generated seam where motion briefly interrupts the ice's stillness and, for just an instant, coaxes it into behaving like something closer to water. And once you start picturing that seam, that thin traveling strip of warmth moving along, wherever the motion goes, a new question begins to surface, almost on its own, a question about whether this heat,
all by itself, is really enough to explain the whole slipperiness of ice, or whether it too, like pressure before it, turns out to be only part of a larger and more layered story.
Let's leave that question hanging for a moment and turn to something more tangible, something you can almost feel under your own feet if you let your mind wander back to the last time you walked across an icy parking lot. Because before we go further into the physics of heat and melting, it's worth slowing down and looking closely at the objects themselves, the humble and not so humble things that carry us across ice, and noticing how differently each one is built, how differently each one touches the surface beneath it, even though from a distance they might all look like they're doing the same simple thing, which is sliding, or trying not to. Start with an ordinary walking shoe, the kind most people are wearing most days without thinking about it at all. The sole of a walking shoe is designed, quite deliberately, to be the opposite of slippery. It's covered in a pattern of small ridges and grooves, sometimes called lugs, sometimes just called tread, and this pattern exists for a very specific mechanical reason. Rubber, the material most soles are made from, is soft and slightly sticky at a microscopic level, and it wants to conform to whatever it presses against, filling in tiny gaps and irregularities the way a hand might mold itself around a stone. On dry pavement, this works beautifully. The rubber grips into the tiny peaks and valleys of the concrete, and friction, in the ordinary everyday sense, holds the foot in place. But ice complicates this picture, because ice, especially the kind that has been walked on and refrozen a few times, is often smoother than concrete by a wide margin, smoother even than the rubber itself in places. The tread pattern that helps so much on dirt or grass or wet pavement finds very little to bite into on ice, and so it becomes almost a spectator, contributing less than we might expect, precisely because there's so little irregularity for it to catch on. This is part of why an ordinary shoe can feel so betraying on ice, so quick to slide out from under a person who has never had a single problem with it anywhere else. It isn't a bad shoe, it's simply a shoe built for a different kind of surface, one with texture instead of an ice sheet's peculiar, deceptive smoothness. Now picture a sled runner, something like the metal strips beneath an old-fashioned wooden sled, or the wider plastic runners under some children's toboggans. A sled runner is a very different shape from a shoe sole. It's long and narrow, often slightly curved upward at the front, and it's meant to carry a good deal of weight, sometimes a child, sometimes an adult, sometimes more than one person piled together and laughing over a fairly small contact area. Because the runner is narrow, the weight pressing down on it is concentrated rather than spread out, which means the pressure at any given point along its length can be meaningfully higher than the pressure under a wide flat shoe sole carrying the same total weight. This matters for the runner's job, because a sled isn't trying to grip the snow the way a walking shoe tries to grip pavement. A sled is trying to glide, and a narrower runner, all else being equal, tends to glide with less resistance than a wide flat surface would, partly because there's simply less material in contact with the snow to drag against it, and partly because that concentrated pressure can, in the right conditions, encourage a thinner film of moisture right along the runner's path. There's also a quieter kind of friction happening here, worth noticing, a kind related to what we were exploring a moment ago, with warmth and motion, because a sled runner sliding steadily downhill is also rubbing, however gently, against the snow beneath it, and that gentle rubbing contributes its own small measure of heat, its own small softening of the surface it travels across,
working alongside whatever pressure effects might also be present. Skis complicate the picture further, because a ski is, in a sense, an enormously stretched out and flattened version of a sled runner, but built with an entirely different set of priorities in mind. A ski spreads a skier's weight across a long, flat area, specifically so that the skier doesn't sink into loose snow the way they would in ordinary boots, floating instead across the surface the way a wide raft floats on water rather than plunging through it. On packed snow or groomed slopes, the underside of a ski is engineered to be extraordinarily smooth, often coated with a wax chosen deliberately for the day's temperature and snow conditions, because different waxes interact differently with the fine structure of snow crystals at different levels of cold, and yet skis are not simply smooth for smoothness' sake. Along their edges, ski designers place a thin strip of metal, sharp enough to bite into firmer snow or ice when the ski is tilted onto that edge, which gives a skier the ability to turn, to slow down, to carve a controlled arc down a slope, rather than simply sliding helplessly in whatever direction gravity happens to prefer.
So a single ski carries within it two almost opposite philosophies at once: an underside built to glide with as little resistance as possible, and an edge built to grip fiercely the instant it's needed, and a skilled skier moves fluidly between relying on one and then the other, sometimes within the same second, tipping the ski just enough to summon that edge into service, and then flattening it again to let the glide take over. Then there's the steel skate blade, which in some ways represents the most extreme and most specialized of all these surfaces, the one built with the narrowest possible contact and the most singular purpose. A skate blade isn't flat across its bottom the way it might appear at a glance. It's actually very slightly hollow, ground with a shallow concave curve, so that the blade meets the ice not along its full width, but along two thin edges, one on each side, running the length of the blade like a pair of parallel rails. This hollow grind, as it's called, is something skate sharpeners adjust deliberately, choosing a deeper or shallower hollow depending on what a particular skater needs. A deeper hollow, biting more sharply for tighter turns and quicker stops. A shallower hollow, gliding more freely with less resistance for skaters who prioritize speed over sharp maneuvering. Because the blade meets the ice along these two narrow rails rather than across a broad flat surface, the pressure concentrated at each rail for a given skater's weight is remarkable, far higher than anything a shoe or even a ski edge typically produces, and this concentrated pressure works together with the friction of gliding motion to help create the thin, fleeting layer of moisture that lets a skater seem to float rather than scrape across the surface beneath them. What becomes clear, laying these 5 objects side by side in the mind, a walking shoe, a rubber sole more broadly, a sled runner, a ski, and a skate blade, is that there is no single universal relationship between an object and ice. Each one strikes its own particular balance among grip, plowing, and gliding, and that balance comes from a combination of factors working together rather than any one factor alone. How rough or smooth the surface is matters. How the weight above it is distributed across that surface matters. Whether the object has edges built deliberately to bite, and how sharp or blunt those edges are, matters enormously. And how the object moves, whether it's dragged flatly forward like a sliding shoe, whether it curves and carves like a tilted ski, whether it travels the narrowest possible line like a skate blade, shapes the whole experience as much as the object's shape does on its own. None of these objects is simply sliding across ice in some generic, interchangeable way. Each is having its own particular conversation with the surface beneath it, a conversation shaped by geometry, and pressure, and motion,
all speaking together, and understanding that conversation, piece by piece, brings us closer to untangling why the same sheet of ice can feel so wildly different, depending on what happens to be standing, or gliding, or grinding to a halt upon it.
Now, let's turn to something that seems, at first thought, like it shouldn't be a variable at all. Ice is ice, surely, and cold is cold. But temperature changes everything about how slippery a frozen surface feels underfoot, and the changes don't move in the simple direction most people would guess. Picture a very cold day, somewhere well below the freezing point of water, the kind of cold where your breath turns visible and hangs in the air a moment before drifting off. You might expect that colder ice would be more slippery, since ice is the thing that makes surfaces slippery in the first place, and more cold should mean more ice-like ice, so to speak. But researchers who study friction on frozen surfaces have found something closer to the opposite. Ice near its melting point, just a degree or two below freezing, tends to be more slippery than ice that has been sitting in deep cold for a long stretch. Ice at 10 degrees below 0 Celsius behaves differently underfoot than ice sitting right at the edge of freezing, and ice at 30 below behaves differently still, often feeling distinctly grippier, almost chalky, almost like fine sandpaper, compared to the glassy quality of ice near the melting point. The reasoning traces back to that same thin layer of moisture we've been circling around this whole time, the slippery film that forms at the surface of ice through some mixture of pressure, friction, and the ice's own surface behaving differently from the solid frozen bulk beneath it. That film depends on molecules at the surface having enough looseness, enough freedom to slide past one another, to behave more like a liquid than a rigid crystal. Near the melting point, the ice surface is, in a sense, right on the edge of becoming water, and it doesn't take much encouragement, a bit of pressure, a bit of friction, the warmth radiating faintly from a passing body, to nudge some of those surface molecules into that loose, slippery, liquid-like state. But deep in cold weather, when the ice sits many degrees below freezing, that surface layer is more firmly locked into its solid arrangement. It takes more energy, more friction, more pressure to loosen it up, and so the same footstep, or the same sliding motion, produces less of that helpful lubricating film. The ice is, in a very real sense, less ready to become momentarily slippery because it starts further from the threshold. This is part of why people who spend a lot of time outdoors, in genuinely frigid climates, sometimes describe deep cold ice as having an almost gritty, trustworthy quality underfoot, something closer to walking on hardened sand than on the treacherous glass of a late winter sidewalk. It is not that the ice has changed its identity. It's still water, frozen solid, still built from the same hexagonal lattice of molecules we spent earlier sections working through, but its readiness to slip into that fleeting liquid state, the state that actually does the slipping, has shifted with the temperature, and that shift is not something most people intuit correctly on their own. There's a related wrinkle worth sitting with for a moment, which is what happens to ice as it warms toward, and eventually crosses, the melting point from the other direction. Ice that sits right at 0 degrees Celsius, wet ice, ice with a visible sheen of liquid water sitting on top of it, behaves differently again from ice a couple of degrees colder that merely feels damp underfoot. Once actual liquid water is present on the surface, in a proper layer rather than just the ultra-thin molecular film we've discussed, the physics shifts again, because now there's enough water for it to behave hydrodynamically, meaning it can be pushed around, squeezed out from under pressure, or in some cases trapped in a way that produces almost no friction at all.
This is the ice that skaters and hockey players sometimes describe as fast, but a little unpredictable. Ice that has begun to soften at its surface, sometimes because the rink has been used heavily, and the friction of many blades has warmed it, sometimes simply because the building's temperature control has let things drift a degree or two higher than ideal. A thin film helps a blade glide. A proper layer of standing water can make things glide almost too well, unevenly, in a way that feels less controlled, more like driving through a puddle than gliding over a hard surface. All of this helps explain why so many different kinds of frozen surface, ones we tend to lump together under the single word ice, actually behave in noticeably different ways, and it's worth taking a slow walk through several of them, one at a time, letting each one settle into place. Snow, to begin with, isn't really ice in the smooth, continuous sense we've been discussing at all, not freshly fallen snow anyway.
It's a loose gathering of ice crystals with huge amounts of air trapped between them, and when you step on fresh snow, you're not gliding across a slick surface so much as compressing and collapsing a network of tiny frozen structures, crunching them together, which is part of why walking on fresh snow can actually feel quite secure, almost grippy, compared to the smooth ice hiding beneath it. It's only when snow gets packed down, walked over repeatedly, partially melted and refrozen, that it starts to develop the smoother, harder character of true ice, and starts developing that same capacity for a slippery surface film. Frost is its own separate case, delicate and thin, a fine coating of ice crystals that forms not from liquid water freezing, but from water vapor in the air, settling directly onto a cold surface and turning to ice without ever becoming liquid first, a process with its own particular name that we touched on earlier in this narration. Frost tends to be extremely thin, often just a whisper of a layer, but because it forms right at the surface of whatever it's coating, a car windshield, a blade of grass, a wooden deck rail, it can create a surprisingly slippery film with very little material, precisely because that thin structure responds so readily to the tiny amounts of pressure and friction involved in a footstep or a fingertip brushing across it. Black ice earns its unsettling reputation honestly, and understanding why circles back to nearly everything discussed so far. It's called black ice not because the ice itself is actually black in color, but because it's so thin, so clear, and so smooth that it lets the dark pavement beneath it show straight through, making a genuinely icy patch of road look, to a driver or a walker glancing down, like nothing more than a stretch of wet asphalt. This kind of ice often forms from a very thin film of water, perhaps meltwater from earlier in the day, or dew, or light rain, that freezes quickly and evenly across a surface without trapping air bubbles or forming the rougher crystalline texture of frost or packed snow. That smoothness, that lack of trapped air, and lack of texture, is exactly the kind of surface that produces the most consistent, most effective lubricating film underfoot, which is part of why black ice has earned its reputation as the most quietly dangerous of all the varieties we've discussed, deceptive to the eye, and remarkably efficient at producing that dangerous, gliding thinness of moisture between a shoe and the ground. Rink ice sits at the opposite end of the spectrum from black ice in terms of how it comes into being, even though both can feel remarkably slick. Rink ice is built deliberately, thin layer sprayed over thin layer, water carefully applied and allowed to freeze in stages, then shaved and resurfaced again and again by machines built for exactly that purpose, all in the service of producing a surface as smooth, as uniform, and as free of air bubbles or embedded debris as is practically achievable. That manufactured uniformity is precisely what makes it so wonderfully cooperative,
with escape blades' narrow rails, offering almost nothing in the way of unpredictable texture to disrupt the glide. Lake ice, meanwhile, forms under circumstances nobody is controlling at all, shaped by wind, by snowfall settling onto its surface before it has fully hardened, by uneven freezing as the water below moves and shifts, by cracks that form and refreeze, by the whims of an entire season's weather rather than a machine's careful passes. And it's to that wild, uncontrolled, endlessly varied character of natural ice, ice shaped not by a groundskeeper, but by wind, and cold, and time, that we can now turn our attention.
The wildness of lake ice, the way it answers to nothing but wind and cold and the slow turning of a season, might seem to place it far outside the reach of careful measurement. And yet it's precisely that unruliness, that refusal to be simple, which has pulled ice into some of the most patient and painstaking laboratories in modern physics, places where researchers have spent decades trying to pin down, at a scale smaller than anything the eye could ever resolve, what is actually happening on the outermost skin of a piece of ice when something slides across it. It helps to picture the scale we're talking about. A single sheet of paper is perhaps 100,000 nanometers thick, the layer of disturbed, softened, liquid-like water that seems to sit atop ice near its melting point is often only a few nanometers deep, sometimes less, sometimes closer to a few dozen, depending on temperature and purity and how close the surface sits to 0 degrees. That's a layer so thin that if you scaled the ice crystal up to the height of a person, the slippery film on top would be thinner than the finest coat of paint, thinner in relative terms than the moisture on a fogged window. Measuring something that delicate, without disturbing it in the very act of measuring, has taken the ingenuity of several generations of scientists and no small amount of specialized machinery. One family of tools researchers lean on are what are called friction rigs, devices built specifically to drag a small probe, sometimes a sphere, sometimes a blade-shaped tip, sometimes something closer to a tiny sled, across an ice surface under carefully controlled conditions, while sensors record exactly how much force is needed to keep it moving. The appeal of a rig like this is its bluntness, in the best sense. It doesn't try to explain why ice is slippery, it simply measures, again and again, under different temperatures, different speeds, different loads, exactly how slippery it is, producing numbers that any theory eventually has to answer to. And what these rigs found, patiently, over years of repeated trials, was not a simple story. Friction on ice doesn't fall neatly with temperature the way early guesses assumed it might. It tends to be relatively high on very cold ice, drop toward a broad minimum, somewhere in the range that a skater or a hockey player would recognize as prime rink conditions, and then, curiously, begin rising again as the ice approaches its melting point and the surface film grows thick enough to behave less like a lubricant and more like actual water, dragging at whatever moves through it, the way wading through a puddle drags at your ankles rather than helping you glide. That non-monotonic shape, that rise and fall and rise again, was itself a discovery, and it quietly ruled out any explanation that relied on pressure alone, since pressure melting predicts nothing like the small warming near the melting point actually eliminates. Friction rigs tell you how slippery a surface is. They don't, by themselves, tell you why. For that, researchers turn to spectroscopy, a family of techniques that essentially involves shining light, often in very particular wavelengths and combinations, onto a surface and reading the pattern of light that bounces back
or is absorbed, the way a doctor might read an X-ray without ever having to open up the body directly.
One especially useful version of this, called some frequency generation spectroscopy, was developed and refined in the latter part of the 20th century, notably in laboratories associated with the physicist Y.R. Shen at Berkeley, and it has a peculiar and useful property. It responds strongly to molecules that are disordered or asymmetrically arranged, exactly the condition of water molecules sitting at a boundary between two different environments, and it responds far more weakly to molecules locked into the fully repeating symmetry of a bulk crystal. Applied to ice, this technique let researchers essentially listen to the very outermost layer of molecules and ask, without touching them, without warming them, whether they were behaving like solid ice, like liquid water, or like something distinctly in between. And the answer that emerged, patiently confirmed across many experiments, was that something in between. Even well below the ordinary melting point, the outermost one or two layers of water molecules at an ice surface show a kind of restlessness, a mobility, that the molecules just beneath them do not share, a finding that gave real experimental weight to what had for a long time been treated more as a useful hypothesis than a demonstrated fact. Alongside spectroscopy, microscopy has offered its own patient window into the same question, though from a different angle. Atomic force microscopy, a technique that involves dragging an almost impossibly fine tip, sometimes only a few atoms wide, across a surface and measuring the tiny deflections as it encounters bumps and dips and softness, has let researchers feel the texture of an ice surface at a scale no human fingertip could ever sense. What they've found is a surface that is not simply flat and hard, the way a countertop is flat and hard, but one with a kind of give to it, a softness that increases as temperature climbs toward the melting point, consistent with a thin, mobile, liquid-like layer sitting atop the rigid crystal beneath. Some of this microscopy work has even managed to distinguish between different faces of an ice crystal, since ice, like many crystalline solids, doesn't present the same arrangement of molecules on every surface. Some faces are more tightly packed, others looser, and this pre-melted layer doesn't behave identically on all of them, growing thicker or thinner, appearing at slightly different temperatures, depending on which face of the crystal a researcher happens to be probing. It's a reminder that even a single word, ice, is hiding a surprising amount of structural variety underneath it. And then there are the simulations, which approach the problem from an entirely different direction, not by measuring a real piece of ice at all, but by building one, atom by atom, inside a computer, using known laws of how water molecules attract and repel each other, and then letting that simulated crystal run forward in time to see what happens on its own. This kind of work, sometimes called molecular dynamics, has grown enormously more capable over the past few decades as computing power has expanded, to the point where researchers, including groups working under scientists like Angelos Michaelides in London, have been able to simulate surfaces containing many thousands of individual water molecules and watch, essentially frame by frame, how the outermost layers begin to lose their orderly crystalline arrangement as temperature rises, well before the interior of the simulated block shows any sign of melting at all. These simulations have been valuable precisely because they let researchers isolate variables that are almost impossible to separate in a real physical experiment, testing, for instance,
What happens to pre-melting if you remove the effect of air pressure entirely, or if you make the surface artificially perfect, free of any of the microscopic steps and defects that real crystals always seem to carry?
What's worth sitting with in all of this modern effort? Friction rigs and spectroscopy and microscopy and simulation together is not a single tidy conclusion, but a kind of layered agreement with edges that are still soft. There is now fairly broad agreement, built from multiple independent lines of evidence rather than any single clever experiment, that ice surfaces do carry a thin, mobile, disordered layer well below the bulk melting point, a layer that behaves in ways meaningfully different from both solid ice and ordinary liquid water, and that this layer plays some real part in why ice feels slippery underfoot. There is much less agreement on the precise thickness of that layer under any given condition, on exactly how it depends on impurities or air pressure or the particular crystal face involved, and on how much of the sliding, gliding sensation we actually feel should be credited to this quiet, ever-present pre-melted film versus the friction-generated melting that happens the instant something moving, a skate blade, a shoe, a sliding boot, adds its own heat to the encounter. That different research groups, using different tools and different assumptions, sometimes arrive at numbers for that pre-melted layer's thickness that differ by a factor of 10 or more, not because anyone has made an obvious mistake, but because the answer seems to genuinely depend on conditions that are maddeningly difficult to hold perfectly steady from one laboratory to the next. It's the kind of scientific unsettledness that isn't really a failure at all, but simply an honest description of how close science has actually gotten to something that, on the surface, seemed like it should have been simple enough to explain in a single sentence over a century ago. And it's with that honest, unfinished quality in mind that we might now turn toward what all of this careful measurement means beyond the laboratory walls, out in the ordinary, unglamorous places where ice actually meets the world, a sidewalk, a windshield, a runway before dawn. With that unfinished quality still in mind, let's walk out onto the sidewalk, or better yet, onto the ice itself, and see what a skater's blade is actually doing when it carries someone across a frozen pond. A speed skater's blade is not a flat wedge. It's ground into a very slight hollow, so that in cross-section, the blade doesn't touch the ice along its whole width, but along two narrow edges, sometimes barely a millimeter apart. That narrowness matters enormously. All the skater's weight, which might be 60 or 70 kilograms, is coming down through an edge so thin that the pressure at the point of contact is very high, even though the force pressing down is nothing unusual. High local pressure, combined with the friction of a blade sliding forward at speed, means that whatever pre-melted layer already exists on the ice gets joined by a burst of friction-generated melting right at the contact line, a slick of liquid water that forms and vanishes almost as quickly as the blade passes over it. The skater isn't gliding on ice exactly, and isn't gliding on a puddle exactly either. They're gliding on something that exists only because they are moving, a film that their own passage keeps recreating, stride after stride, the way a speaker's voice exists only while they're speaking. This is part of why the shape of the blade has mattered so much to skaters and skate makers going back centuries, long before anyone had a word for pre-melting or frictional heating. Early ice skates, the kind used in the Netherlands hundreds of years ago, were often made from animal bone, tied to the foot with leather straps, and skaters pushed themselves along with poles rather than the pure, edge-to-edge glide we associate with skating today. Bone doesn't hold as fine an edge as steel, and it doesn't concentrate pressure the same way, so those early skaters were working with a cruder, blunter version of the same physics, coasting on whatever thin liquid layer they could manage to summon. When iron and then steel blades came into wider use, skaters could grind narrower, sharper edges, concentrate more pressure into less contact area, and glide with less effort. The improvement wasn't really about the metal being harder. It was about the metal allowing a shape that made the ice cooperate more readily, that pulled more liquid to the surface exactly where it was needed. Skiing works on a related but not identical set of principles, and this is one of the places where the layered, still soft science from before becomes genuinely practical rather than just academic. A ski doesn't concentrate pressure into a razor edge the way a skate blade does. Instead, it spreads a skier's weight across a long, wide, flat surface, which means the pressure under any square centimeter of ski base is much lower than under a skate blade, and pressure-driven melting plays a smaller role. Speed and friction matter more here, along with the wax. Ski wax isn't primarily there to make the base slippery in some simple, direct sense. It's there to manage how the base interacts with that thin surface water, repelling it in some conditions, so the ski doesn't get sucked down by suction into a film that's briefly too wet, and helping generate just enough of it in others when the snow is cold and dry and needs a bit of encouragement to lubricate the glide. This is why cross-country skiers and their wax technicians pay such close, almost superstitious attention to the exact temperature and humidity on race day, because the friendly liquid layer they're relying on behaves differently by a few degrees, and what works beautifully at one temperature can turn sticky and slow at another. Curling asks the ice to behave in an even stranger and more specific way, because a curling stone needs to travel in a straightish line and also, when given a spin, drift gently sideways over its journey down the sheet. Curling ice isn't smooth in the way a skating rink is smooth. Ice makers deliberately spray fine droplets of water across the surface that freeze into a texture of tiny bumps, called pebble, and the stone rides across the tips of that pebble rather than across a continuous flat sheet. This changes the contact area dramatically, concentrating the stone's weight onto countless tiny points rather than spreading it across the whole running band on the bottom of the stone, and that concentration is part of what lets a well-thrown stone travel so far with so little push and curl as it does, though the exact reason a spinning stone curls the direction it does remains, even now, a topic that curling physicists and armchair enthusiasts argue about at some length, with more than one proposed explanation and no single one universally accepted. Glaciers move on a time scale almost impossible to picture while lying still in the dark, but the same underlying gentleness is at work. A glacier isn't rigid the way a block of ice on a countertop feels rigid. Under its own tremendous weight, deep ice deforms slowly, and at its base, where the glacier presses against rock, pressure and geothermal heat and friction from the grinding movement itself can maintain a thin layer of meltwater, letting the whole enormous mass slide almost imperceptibly over the land beneath it. It's the same idea as the skate blade, stretched out from a fraction of a second to a span of years, from a narrow steel edge to a slab of ice that might be a kilometer thick, quietly demonstrating that the story of pressure and thin films of water isn't confined to winter sports at all, but reaches into the shaping of entire landscapes. Down at the scale of everyday life, this same knowledge shows up in far less poetic, but no less useful places. Road salt works by disrupting the way water molecules want to arrange themselves into an orderly crystal, lowering the temperature at which ice can form or persist, so that a road sprinkled with salt might stay wet rather than freeze, even on a night cold enough that untreated pavement would turn to glass. It isn't melting ice by warming it, not in the way a stove melts butter. It's changing the conditions under which ice is stable at all, nudging the whole equilibrium toward liquid, even at temperatures where plain water would freeze. Sanding trucks take the opposite approach and don't try to change the ice's chemistry at all. They simply scatter grit and small stones across the surface to interrupt that dangerously smooth, low-friction film, giving tires and boots something rough and irregular to grip onto, instead of a slick, continuous sheet. Airport de-icing procedures often combine both ideas at once, spraying heated fluid to clear existing ice and a different, thicker fluid to prevent new ice from bonding to a wing's surface during the critical minutes before takeoff, when even a thin, invisible layer of ice on a wing can change how air flows over it in ways engineers take extremely seriously. Tire design leans on the same physics, quietly, every winter. A winter tire's rubber compound is formulated to stay flexible at low temperatures, rather than stiffening the way summer rubber does in the cold, because a stiff tire can't mold itself into the tiny irregularities of a road surface and press through whatever thin liquid layer sits on top of the ice, while a soft, pliable one can. The tread pattern helps too, with fine slits, called sipes, that give the rubber countless small edges, each one acting a little like a miniature skate blade, concentrating pressure and helping to channel away the thin film of water so the rubber can actually touch something solid underneath. And then there are the small, unglamorous habits people develop for simply walking across a frozen parking lot without incident. Habits that turn out, on reflection, to be little folk applications of everything we've just wandered through. Shortening your stride, keeping your weight low and centered rather than reaching forward with each step, walking a little like a penguin, as some cold climate advice likes to put it. All of this reduces the sideways shear force at the point where your foot meets the ice, the very kind of force that a thin lubricating film is least able to resist. It isn't really about being cautious in some abstract sense. It's about working with the same narrow, humble physics that lets a skater glide and a glacier creep, rather than against it. And it's worth pausing here, in the quiet space between one idea and the next, to consider how much of what feels like ordinary caution is really just an unspoken understanding of a molecule's willingness to let go. Let's slow down for a moment and gather up the loose threads, because if you've been listening closely across this long, quiet drift through ice and friction and gliding blades, you may have noticed that no single explanation has managed to carry the whole weight of the story. That's not a failure of the story. It's a clue about how the world actually works, and it's worth sitting with that clue for a while before we go any further. For a long time, the explanation most people learned, if they learned one at all, was pressure. The idea felt tidy and satisfying. A skater's blade presses down on the ice with enormous force, concentrated into a thin edge. The pressure lowers the melting point of the ice right at that spot. A sliver of water appears, just long enough to glide on, and the whole performance resets itself with the next stride. It's the kind of explanation that fits neatly into a single breath, which is probably part of why it spread so widely and lodged itself so comfortably in textbooks for so many decades. The trouble is that the numbers don't cooperate the way the story needs them to. A person's body weight, even concentrated onto the narrow edge of a skate blade, only lowers the melting point of ice by a small fraction of a degree, something like 1 degree Celsius at most, and usually less. That's a real effect, and it's not nothing, but it's nowhere near enough on its own to explain how skaters glide comfortably on ice that's 10 or 20 degrees below freezing, ice so cold that pressure melting would need to perform a feat of arithmetic it simply isn't capable of. If pressure alone were the whole answer, very cold ice should feel like glass underfoot, all grip and no glide, and yet it doesn't, not entirely, and that gap between what the simple theory predicts and what actually happens outdoors on a frozen pond is exactly the kind of gap that keeps careful scientists awake at night, in the best possible sense. So the mind reaches, understandably, for the next tidy story, which is the idea of a thin layer of liquid water that simply sits on the surface of ice all the time, quietly waiting, regardless of pressure or temperature or anything else. This is closer to correct, but it still oversimplifies in a way worth gently correcting. That surface layer isn't a fixed, dependable puddle you can count on in every circumstance. Its thickness changes enormously, depending on temperature, thinning down to something almost negligible, maybe only a molecule or two deep, once you get very far below freezing, and swelling to something more substantial, closer to the melting point. At extremely cold temperatures, the kind you'd find in the upper atmosphere, or deep in a polar winter, this liquid-like layer can become so thin that it behaves less like water and more like a strange, in-between substance, still mobile, still capable of letting things slide, but no longer resembling the pool of liquid that popular explanations often imagine. So the idea that there's always a generous film of water cushioning every surface between skin and ice, or blade and ice, isn't quite right either. Sometimes the film is there and substantial. Sometimes it's barely there at all, and something else has to be doing more of the work. Which brings us to a distinction that's easy to blur, but genuinely matters. The difference between smoothness and slipperiness. It seems, on the surface of it, like these should be the same thing, since a smooth surface feels slippery under your fingers, and a rough one feels like it should grip. But polished marble is smooth, and can still offer plenty of traction when it's dry, while a rough patch of ice, jagged and uneven to the touch, can still send your feet flying out from under you the moment your weight lands wrong. Slipperiness isn't really a property of how flat or textured a surface is at the scale your eye can see. It's a property of what's happening at the interface, at that impossibly thin boundary where one surface meets another, and specifically, whether something at that boundary is willing to shear, to slide sideways under load, rather than lock together and resist. Ice can be rough in shape and still slippery in behavior, because the thing making it slippery isn't its geometry so much as the mobility of whatever thin, almost imperceptible layer sits right at its surface. That layer can exist on ice that looks bumpy to the eye just as easily as on ice that looks glassy, because the eye is measuring something different from what the foot is feeling. And this is where the last misconception gently unravels too, the comforting notion that there must be one single mechanism, one clean, universal reason, waiting to be discovered, that explains why ice is slippery
In every circumstance a person might encounter it. Some corners of this puzzle really have been settled with reasonable confidence, and others are still being investigated, sometimes revised, sometimes narrowed, by researchers working right now with better instruments than anyone had even a few decades ago.
What the evidence, uneven and evolving as it is, does seem to support fairly consistently is something more layered and less catchy than a single explanation, which is that different mechanisms take the lead role under different conditions, handing the baton to each other rather than one mechanism doing all the work alone. Near the melting point, where ice is, in a sense, already flirting with becoming water, that naturally occurring surface layer is thick and mobile enough to do most of the explaining by itself. No blade pressure required, no friction heating required, just the ice being close enough to its own melting behavior that its outermost molecules are loosely organized and easily disturbed. Move colder, into the range where most winter sidewalks and frozen lakes actually sit, and friction starts to matter more. The rubbing of a shoe sole or a blade edge generating just enough heat at the point of contact to soften or thin that surface layer further, assisting a process that pressure and ambient temperature alone can't fully account for. Move colder still, into the deep, dry cold, where the atmosphere itself feels different against your face, and you're relying on something closer to that intrinsic, quasi-liquid layer behaving almost independently of friction or pressure, because there the physics starts to resemble something closer to the strange surface chemistry of the ice itself, molecules at the boundary that are simply less constrained than the molecules locked into the crystal underneath them, regardless of what's sliding across the top. Speed complicates the picture further, and it's worth sitting with that complication for a moment rather than rushing past it, because speed changes how much friction-generated heat accumulates at the contact point in a given instant. Move slowly across ice, and there's more time for whatever heat is produced to spread out and dissipate into the surrounding cold, never building into anything substantial. Move quickly, the way a hockey skate or a fast ski does, and heat has less time to escape, more chance to concentrate right where it's generated, which is part of why the felt experience of skating fast can be so different from the felt experience of shuffling slowly across the same patch of ice. None of this fits into a single sentence you could hand someone as a complete answer, and that's precisely the point worth carrying forward into sleep tonight, that the true picture isn't a flaw in the science or a gap waiting to be closed by one clever experiment, but a genuine reflection of how nature so often behaves, refusing to hand over one tidy rule and instead offering a shifting balance of contributing causes, each one stepping forward exactly when the conditions call for it, and quietly stepping back when they don't. It leaves us, in a strange and rather comforting way, back at the beginning of this whole long unwinding, standing again at the edge of that frozen pond, except now equipped with a little more patience for complexity and a little less hunger for a single, satisfying answer. And from here, with the misconceptions gently set aside rather than forgotten, there's room to turn toward something quieter still, the question of what, after all this wandering through blades and wings and molecules, still remains genuinely uncertain, genuinely open, waiting for someone patient enough to keep looking. So let's turn toward that quiet remainder, that thin residue of uncertainty that no amount of careful explanation has managed to dissolve, and let's do it slowly, the way you might lower yourself into a chair after a long day. No rush to get anywhere, just settling. What science can say with real confidence is that ice, almost all of the time, at almost any temperature you're likely to encounter walking outside on a winter morning, carries a thin, disordered layer at its surface, a skin of molecules that behave less like a rigid lattice and more like something caught in between solid and liquid. This isn't a guess dressed up as fact. It's been observed, measured, probed with instruments far more patient than human senses, going back to studies in the middle of the 20th century and refined many times since, using tools that can watch how molecules at a surface scatter light or electrons differently than molecules buried deeper in the crystal. That disordered layer exists on ice, sitting quietly in a freezer, untouched, no skate anywhere near it. It exists because a crystal's outermost molecules are always missing neighbors on one side, always a little more free to wobble, and water molecules, given even a small amount of freedom, tend to take it. What's still genuinely debated, and this is worth resting on for a moment because it's a rare thing to be told honestly, is exactly how that layer behaves under different conditions, how its thickness shifts with temperature, how it responds when something presses down on it or drags across it, and how much of what we feel as slipperiness on any particular icy morning comes from that layer alone versus from the added contributions of pressure, of friction heating, of the sheer mechanics of a hard object meeting a hard surface at speed. Researchers have spent decades narrowing these questions, and the narrowing has been real progress, not stalling. But narrowing isn't the same as arriving. Different experiments, using different methods, on different kinds of ice, at different temperatures, have sometimes returned numbers for that surface layer's thickness that don't agree with each other as neatly as anyone would like. Some techniques suggest the layer might be only a few molecules deep at very cold temperatures. Others, measuring differently or under different conditions, suggest something thicker. This isn't a sign that anyone did the work poorly. It's a sign that measuring something so thin, so close to a boundary, on a material that changes even as you try to observe it, is simply hard, in the plain, honest sense of that word. There's a kind of relief in accepting that, actually, if you let yourself feel it. We are so often trained to want the tidy paragraph, the one clean cause, the sentence you could repeat at a dinner table and have it land as a complete little fact, quotable and closed. Ice is slippery because of pressure melting. Ice is slippery because of friction. Ice is slippery because of a special surface layer. Each of those sentences, said alone, said as though it were the whole truth, is a small distortion of something larger and more patient than any single sentence can hold. And once you notice that, once you actually sit with it, rather than brushing past it, toward the next fact, something in the mind can loosen its grip a little. Not every question needs to resolve into a single answer to be worth asking. Not every mystery is a locked door waiting for the right key. Some are more like a room you keep returning to, each time noticing something new in the light, without ever needing to declare the room finished. Think again of that skater from earlier, if you like, gliding across a frozen pond somewhere, blades catching the faint gray light of a winter afternoon. Beneath each blade, there's contact, real physical contact, metal meeting crystal, and in that contact, several things are happening at once, in proportions that shift slightly with every stride. There's pressure, concentrated onto a narrow strip of steel, doing a small amount of work on the ice beneath it, though modern understanding suggests this effect is more modest than the old textbook version claimed. Nowhere near enough on its own to explain the whole experience of gliding. There's friction, the simple mechanical rubbing of blade against surface, generating a small measure of heat as the skater's motion converts into warmth
right at that narrow line of contact. More heat, the faster they go, less as they slow, the heat itself shifting with speed, in a way that means no single amount of friction tells the whole story either. And underneath both of those, quietly, whether the skater is there or not, whether anyone is moving across the ice at all, there's that native surface layer, those looser molecules at the boundary, present, simply because ice is ice, because any crystal ends somewhere, and its edges are always a little different from its depth. None of these three explanations cancels out the others. None of them is secretly the real answer, while the rest are decoration. They layer together, they blend, their relative importance shifting with temperature, with speed, with the material sliding across the surface, with how cold the day is, and how hard the object pressing down happens to be. A physicist studying this on a very cold, very still block of laboratory ice, with a slow-moving probe, might find the natural surface layer doing almost all of the explanatory work. A skater at speed on a rink, kept just below freezing, might find friction heating, carrying much more of the burden. Someone studying, a heavy sled runner, under enormous weight, might find pressure, though modest, still adding something meaningful to the mix. The question was never really which one is correct. The question, properly asked, is always, which one is correct here, under these particular conditions? And the honest answer keeps changing its emphasis, depending on where you stand and what you're sliding. There's something almost gentle in that shape of knowledge, if you let yourself see it that way, instead of as a frustration. It resembles, in its way, how so many ordinary things in life turn out to work, not through one dominant cause, but through several modest ones cooperating. None of them loud enough to explain everything alone, all of them quiet enough to be easy to overlook. A good night's rest isn't caused by only darkness, or only stillness, or only the settling of a tired body, but by all of these arriving together, each doing a small, unremarkable part. Ice, it turns out, keeps something of that same humility built into its physics. It doesn't want to be reduced to a single cause any more than sleep does. And so, if the mind is still turning gently over blades and molecules and the shape of a hexagon locked in frozen water, there's nothing left to solve tonight, nothing left to hold on to. The pond is still out there, somewhere, in the dark, its surface catching whatever faint light manages to reach it, its molecules arranged in their patient six-fold pattern, its outermost layer a little looser than the crystal beneath, waiting without waiting for morning, for someone's boots, for the scrape of a blade that may or may not come. It doesn't need an audience to keep being what it is. It was slippery in that quiet, layered way long before anyone thought to wonder why, and it will go on being slippery in that same unhurried, many-caused way long after the wondering has drifted off into something softer. Let the picture blur now, if it wants to. Let the careful distinctions between pressure and friction and surface disorder loosen their edges, the way any clear thought does when sleep is finally close enough to touch. There's no need to hold the explanation tightly anymore. No need to keep it lined up in neat order the way it might have felt useful to do earlier in the evening. The ice will still be slippery whether or not the reasons stay sharp in memory by morning. The pond will still be there, still quiet, still cold, still patiently ambiguous in exactly the way real things so often are, underneath whatever question anyone brings to it. So let the blades and the crystals and the shifting proportions of cause settle now, the way anything settles when it's finally allowed to rest, without needing to resolve any further, without needing to be understood all the way to the bottom before it's allowed to be set down for the night. Rest well.